very few places anywhere in the world where in the span of 6 or 7 miles, you can go from these rocky, chaparral-covered ridgetops to the deep sea. So that there's this compression of life zones and diversity that is almost unparalleled. You know, Elkhorn Slough is the intersection of all sorts of interesting issues. Groundwater, animals living in the sediment, carbon sequestration. So almost any kind of question that somebody's interested in how the world works or how to make it better, this is like a perfect laboratory to do that.
We're trying to understand under what conditions can we maximize the sequestration of CO2. Wetlands and sloughs are amazing ecosystems. They are so biodiverse. And specifically, you know, we want to restore wetlands because they're important for multiple purposes: wildlife, for water, and for combating climate change. The reason wetlands are important for climate change is because they're one of the only ecosystems that can take out carbon dioxide from the atmosphere and store it in the soil for thousands of years. So we want to restore and design wetlands that maximize the carbon dioxide removal, minimize methane emissions, while providing other ecosystem services. And using measurements, we can actually calculate the carbon balance and understand how efficient the wetland is in sequestering carbon dioxide.
I'm part of this larger wetland carbon dynamics project, and I primarily focus on the lateral carbon transport in the surface waters and looking at the surface water quality. So these are the ISCO automated water samplers. I've got one out at each of our 5 sites. They are basically like a pump on a timer, and they fit 24 bottles so that I can get a full tidal cycle of water samples without having to physically be out here collecting water every hour. It's got this arm on the other side, and this will rotate every hour and pump up some water from the surface. And then I analyze all of mine for dissolved inorganic, organic carbon, total alkalinity, nutrients, and particulate organic carbon. These 3 are wells that I have installed at 3 different depths. So I have in each of them a sensor installed that will take salinity, conductivity, temperature, and pressure every 15 minutes. Wetlands in general, sloughs included, are really effective at sequestering carbon because as the vegetation that grows within them dies, it doesn't decompose because it falls into this anoxic, so really low oxygen environment because of the standing water. The eddy covariance towers are basically a sensor array mounted a couple meters above the soil that will sense wind speed, temperature, a couple of different meteorological variables, and concentrations of gases. And then some of our project scientists will take that data and look at how gas exchanges with the atmosphere.
What we're doing here and why we have so many towers in so many different places is to get a better representation of what wetlands are doing across the Elkhorn Slough. And then we can take that data and upscale it by applying it to other wetlands that are in a similar zone, whether it's in California or, you know, kind of globally as well, to see, well, if this wetland is behaving like this, are other wetlands behaving like this? We're looking at the incoming data stream from the tower itself. We're getting a good signal strength for our CO2 sensor as well as our methane sensor, and yeah, we're getting good readings right now.
So to get like a complete image of what carbon is doing in the slough, we also need to know what is happening in the subsurface. And to figure that out, we take sediment cores where we analyze both the sediment and the pore water to figure out what's happening. With these syringes, I'm essentially getting the pore water, and in this pore water I can figure out what molecule the carbon is in, and then based on that I can hopefully extrapolate what kind of like microbial processes or transport processes or other reactions are governing how the carbon is moving and changing. It's like a big puzzle. I like getting all the pieces and then trying to put them in the right spot.
Here we go. It's like quicksand. It's like quicksand.
The major driver of climate change is human-induced and release of carbon dioxide to the atmosphere because of our energy consumption and our lifestyle. And as there's more CO2 and other greenhouse gases in the atmosphere, heat is trapped in the planet, resulting in increases in temperature. And with increases in temperature, there's all sorts of effects to human and the ecosystems around us, from heat waves, increased hurricane intensity, sea level rise, ocean acidification. Unfortunately, we have very few intact wetlands left in California, in the US, or in the world in general. Over the years, people have converted wetlands into agriculture land. They drain them, dry them, use them to grow crops. So in California, about 90% of the wetlands are gone when we compare to the 1900s.
One of the natural climate solutions that we're looking at is trying to rehabilitate or protect marshes because they're so effective at storing carbon. So if our research can highlight one of these benefits of marshes and get people interested and have funding and policy around protecting and restoring marshes, I think that would be the main goal.
This concept of blue carbon, so carbon that's sequestered in shallow coastal waters. No oxygen penetrates these soils, so there's nothing to break down the carbon. So it basically is frozen in time. And there are places around the world where you can measure thousands of years of carbon trapped in these ancient layers of marsh, mangrove, and eelgrass. I think Adina is a great example of a professor who is taking advantage of this place and understands what a great learning opportunity this is for her students. That's what this place is for. And so I think, it tickles me when I see Adina and her students out here doing the work, getting muddy, that they're learning a lot, and I hope having fun.